to introduce Marie Doumic, who is a researcher at INRIA, the French National Institute for Research in Applied Mathematics and Computer Science. Marie did her PhD in 2005 about modeling laser propagation in plasma. And after working as an engineer for a few years, she joined INRIA and became a researcher in mathematical biology. Her research field is structured population models, mainly by means of PDEs for growing and dividing populations. She is an expert in modeling cell division and protein polymerization occurring in amyloid diseases. In 2012, she was awarded an ERC starting grant. She has supervised 10 PhD theses, I think, and she is an editor of different journals and the coordinator of the Mamba project team, which belongs to INRIA, CNRS, and Sorbonne University. So we are really happy to have her as a speaker of the colloquium today, where she will give the talk entitled Structured Population Equations from Qualitative Modeling to Experimentally Validated Models. So please, Marie, whenever you want.
Thank you very much, Sylvia, for this very nice introduction, and thank you for the invitation. It's really a pleasure to speak for ESMTB, and I think I owe much to this beautiful society. So I will try to review a kind of results which date back from almost a decade now, but trying to show you also the very recent results and the open questions which remain and which are still really many. So all the framework of my talk is growing and dividing populations without any consideration on space, not in this talk at least, but it is of course considerations which are now more and more interesting. And two applications as a guideline. First, protein aggregation and fragmentation, which may occur, for instance, in the so-called amyloid diseases, and a special focus on fragmentation. And the second application, cell division cycle, with a special focus on bacteria. Yes, just I wrote it, a new, very recent application, mutation, because it appears that sometimes mutation may occur according to some equation which resembles a lot the fragmentation equation. And for each application, it is more or less the same steps that we follow. Typically, there is a part of modeling, which is we formulate a data-driven inverse problem, trying really to fit to the question, what do I observe? And from these observations, what should I be able to estimate and find? For the modeling parts, you can use either the stochastic modeling or partial differential equations, and both are, of course, very closely linked, which I will also show you. And then the analysis of the models, all the most theoretical parts really plays a very important role here, because it is thanks to the analysis that you will be able to really say something interesting about the inverse problem. Put everything in a machine and waiting that the machine answers you will not give you much insight on the real mechanisms which underlie your problem. And finally, of course, inverse problem solution and back to the data to validate or to invalidate your assumptions. Okay, I just have a small problem. Okay. So let's go for all these steps one by one. First, the motivation. Our two problems. First one, protein polymerization. So protein polymerization, of course, happens, and polymerization in general, there are so many fields of application that I will not detail everything, but especially in the so-called amyloid diseases, it is what characterizes all of them, which are Alzheimer's, prion disease, mad cow disease, Huntington's, Parkinson's, etc. In all these diseases, you have an abnormal accumulation of protein aggregates called amyloids, and which cause the disease to occur. The problem is that we don't know much about how they aggregate to one another. And also, the phenomenon of fragmentation is thought to be very important for the propagation of the disease and the infectious character of some of them, like prion disease. So here you see some experiments carried out by our collaborator Wei-Feng Zhu, which is really key in all these parts of the talk. It's also a part which is done with Miguel Escobedo in Bilbao and Magali Tournu in Marseille. So here what you see from left to right, it is the time dynamics of two different proteins. One is alpha-synuclein and the other beta-lactoglobulin. And at the beginning of the experiment, you have very long filaments that you see here. On the top, on the inset here, you have a zoom of the rest of the window. And the biologists agitate the filaments so that they break down into small pieces. And as you can see, they become smaller and smaller. And our question is, how can you estimate the main characteristic, the main features of the fragmentation from such images? To do so, let me give you some hints, some first hints about models. So for this part, I will stick to PDEs, and we can write a partial differential equation for the distribution of filaments. So typically, you think when you see these images that at several time points, T1, T2, etc., you measure samples of proteins, of filaments, having different sizes. Okay, so here you see, at the beginning, you have not so many samples, so it's not so many fibrils, and at the end, many more, of course. And so for this, and this sample, x1, x2, xn, you can assume that it is a sample of IID variables, of realizations of IID variables, which have for density n of tx, and n of tx is the solution of the following partial differential equation. So what is this equation? You have dn over dt, which is the evolution of the number of polymers at time t of size x, which is equal to first degradation term, meaning that the particles break down into smaller pieces with a total fragmentation rate b. So you have this term minus b of x n of tx. And they can also be created by larger polymers which have been broken down. So this is this integral from x to infinity of what? B of y n of ty. It is the proportion of polymers of size y which have divided into smaller ones. And this kernel k of yx, which means that you have a probability distribution saying that polymers of size 1 probability to give rise to a polymer of size x. And in this equation, typically, what you measure is n of tx, at least up to a noise, of course, since here it is a sampling noise and a measurement noise also. And what you are looking at is not the solution of the equation n of tx, it's the parameters b of x, the fragmentation rate, and also the fragmentation kernel k of yx. And why is it important to estimate them? Because it will allow you to understand how all these dynamics occur, okay? And in particular, for these proteins, it will allow you to know, for instance, for the fragmentation kernel k of xy, is it more important at the edges of the polymers, meaning that the polymers break down really at the boundary, or on the contrary, is it stronger in the middle of the fibrils? For the fragmentation rate B, why is it important? Because it's important to know whether the larger polymers, the larger fibrils, break more or break less than the smaller ones. Because knowing that, you will know which ones are the most infectious, the most dangerous being the ones which will break down faster, because then they can regrow also faster, leading to an exponential growth of the total population in presence of small monomers. So for this fragmentation equation, you have two very important facts, very easily found when you look at it, which gives you a flavor of the total dynamics. So first, it is a conservative equation, meaning that the total mass you see here, the total mass has not changed during the experiment. You have the same total amount of polymerized mass at the beginning and at the end. It is the number of fragments which is increased. So when you integrate the equation against the weight x here, you will find that d over dt of integral of x n of tx dx is constant. It means that for the fragmentation rate and kernel, you have this equality, integral of x b of x n of tx equal integral of x k of yx b of y n of ty dy dx. Hence, the fragmentation kernel is not anything. It is something which has to satisfy the mass conservation, which means integral from 0 to y of x k of y dx equal y. And in the specific case of binary fragmentation, meaning that you consider only the polymers which break down into two pieces, then you have a symmetry k of yx equal k of y minus x. Because when you create a polymer of size x, you also create another one of size y minus x, so that the total mass is conserved. And two really very important cases, which are first, uniform fragmentation. It is when k of yx is constant for x smaller than y. And another one, it is a uniform kernel, and the so-called diagonal kernel, which is also the equal mitosis kernel, when on the contrary, you allow the polymers to break down only exactly in the middle. And in such a case, you have k of yx, which is a delta Dirac, 2 delta Dirac in x equal y over 2. And these two specific cases are part of a more general specific case also, which is the case of self-similar fragmentation. I have written it here. It is when k of yx depends only on the ratio of x over y, meaning it depends only on the relative place where it breaks down. It is an assumption that we always do, almost always. We shouldn't, but we need some simplifications, you know, because why? In reality, I think we do this assumption mainly for mathematical reasons, because it is not so easy to justify physically or biologically. But to date, what we observe is not always rich enough to really estimate a k of yx. So this allows really nice analysis, as you will show later on. And also, I mentioned that physicists also very often do this assumption, and typically for the same reason as mathematicians. So this is for the first, here it is for the first application. Now let me have a look on, so just a minute, I have a small problem. If I do, yes, I can do like that, yes. So here it is a video for the second application, which is bacterial growth, or more generally, cell division cycle. So here what you see at the beginning of the video, it is a bacteria called Escherichia coli. I think many people know it here. So what does this bacteria do in this video? There is much nutrient in a large excess. So each bacteria grow, and after a while it divides, and then can grow and then divide. And if you think a little bit of this type of data, you see, you observe much more. Before, you observe only some snapshots at several time points for proteins. But now with bacteria, it's really much more, because you know exactly which bacteria has divided into which one. You know who is the mother, who is the daughter. You know the speed of growth, and you know also the speed of division. So the questions we may ask are really much richer. but also a bacteria is a much more complex organism. So it's a good thing that we can answer to more questions, because the machinery inside a bacteria is of course not the same than inside a simple protein polymer. So the question typically is, how can we build a model which would really be quantitative for this type of division? So as I said, you have really much richer data as for proteins, and you have two types of data for bacterial growth. In this video, as you have seen, you observe all descendants of one given cell till a certain time, and you observe it for several microcolonies. But you also have a second type of data, which I will show you now. It is here, what is called the mother machine. I think it has become very popular, so probably many of you know what it is. It is when you make bacteria or cells grow in several microchannels. So you see here, it is one microchannel. And what is very clever in this machine is that you keep only one daughter cell at each division, because the daughter cell pushes the other, and at the end, it goes away in a big channel, so that you can observe genealogically the lineage of a cell for, I don't know, 100 generations, which is totally impossible, because try to do 2 power 100 and you will immediately understand why it's not possible to observe a full population of bacteria during 100 generations. So I've cited this paper from Robert et al. Lydia Robert is also a very important, the biologist collaborator for this part of the talk. It's a paper of 2010, and it's really, this last decade, it has become increasingly popular, and I think many labs now develop such microchannels, called also the mother machine, okay? And of course, the mathematical model you will choose depends on this type of data. It will not have the same model exactly. I will detail this afterwards. So first, when you have so rich data, you can do much directly from it. And before writing an inverse problem, let us wonder on what we can say directly by direct observations. First, we can say that the daughter cell size, in this case of Escherichia coli, not for any type of cells, of course, is approximately half of the mother cell size. What I call size is the length of the bacteria. Second, we can really measure the growth rate of each cell. So there was much debate among biologists, but at a first glance, and for this talk at least, we can consider that each cell grows exponentially, meaning a linear growth rate. So if x here is the size of one cell, you have dx over dt, which is equal to kappa times x. And we neglect the variability so that every cell have the same kappa, okay? Of course, we can refine the model afterwards. We assume that there is infinite nutrient and space, so the growth is not limited. And we pick up the first cell at random. And more important, no memory. I mean, once you have all the desired characteristics of one cell at birth, all what concerns the mother is forgotten. It's the Markov property. But can you really observe the decision which makes a cell divide? Of course, a cell doesn't really decide to divide, but I mean all the machinery. This cannot be observed directly from such a video. And typically, the question we will ask now is what triggers bacterial division? So our first question, the most natural one, and which was the only alternative for a long period of time, it is, does a bacteria decide to divide according to its size or according to its age? Or of course something else. So this gives rise to the whole field of structured population dynamics. According to what you decide, you will have a model structured differently. if you decide that your cell divides according to its age, you will have all the field of age-structured renewal equation or renewal process. If it's according to its size, you will have a size-structured equation or a growth fragmentation equation, the same equation as for proteins, except that you have had growth rates which was not present, of course, for the polymers, or something else. And I already spoils the finding, which is that in 2015, there have been 2 papers or even 3 papers, I think, of biologists who have found that better than size or better than age is what is called the increment of size, meaning it is the cells will decide to divide according to the difference between its age at its size at division and its size at birth. So I will detail this last model also. And the question is, can we really deduce laws from our observations? And with such data, is it possible to decide which model is the best? So 2 main modeling framework, as I introduced at the beginning, either stochastic processes where you model really each cell, or partial differential equations where you model the whole population, or other said, you model an average behavior of one given cell. So let's go on for first the stochastic processes, which is maybe more intuitive, certainly more intuitive for biologists at least. And also it's an excellent way to have some intuition on what is happening. So typically the field, you may model this by what is called a piecewise deterministic Markov process. So you start with a single cell of size x0. The cells grow deterministically. This is why it is called piecewise deterministic. So you have dx over dt equal kappa x, and x of time 0 equal x0. And at each moment, you have an instantaneous probability rate b to divide. And this division rate b will depend on the structuring variable you choose. Once it divides into 2 offspring. So to simplify, I consider here 2 offspring of equal size. So their size is x of t0 over 2. And since I have assumed an exponential growth of individual cells, x of t0 is equal to x0 exponential kappa t over 2. Okay. And then the 2 offspring start independent growth. It is a Markov property according B and according to what you have chosen for. Okay. So you can put all this information into a random tree. So what is this tree? It follows genealogically all your cells. So here it is big U. I have denoted it it's 0, 1 power n. So n represents a generation. And you begin with this, with the very first cell, it is the empty set, okay? And to each node U, you associate a cell with size at birth, XU, and lifetime zeta U, and any other characteristic variables that you want. And if U minus denotes the parents, then I simply rewrite the same law. You have XU, which is equal to XU minus over 2 exponential kappa zeta U minus, okay? Really elementary at this stage. You have an equivalent view to this stochastic branching tree. It is given by random measures. So here, what you look at now is you look at the cells which are alive at a given time, t. So it's no more a genealogical view. It is rather a time-dependent process. So at one given time, t, you count all the cells which are alive. And you consider that you have a random measure, m of xt, which is given by the sum on all the alive individuals of delta Diracs taken at this point. So here, if it is a size, it is the sum of delta at xi. If it is age, it is the sum of delta at age ai, etc. And here, remember the 2 experiments. two cases. So either you have the mother machine, only one cell at a time. Then the total mass is conserved at each time, and typically you have only one Dirac mass, delta xi, at a given time t, okay? If you have the whole population, it's different. Of course, the number of cells and of Dirac masses increases exponentially. Now let's look at the simplest model, the age renewal, the age model, the renewal process, okay? So then to finish your model, you need to put some assumptions on the division rates. Here I have assumed that it divides according to the age of the cell. It means that the probability of zeta u, which is the lifetime, is larger than a, is equal to the exponential of minus integral from 0 to a of b of s ds. This is really elementary for renewal processes, okay? And then I can look at the mean empirical distribution. And it is well known that if you look at this quantity, which is the expectation of the sum of f of ai, which is f against the empirical measure, the sum of delta Diracs, then in a weak sense, you obtain PDE. Typically here, you obtain the renewable equation. So you have dTn plus dAn, which is equal to minus b of a n of ta. Maybe you remember the fragmentation equation at the beginning. It's really the same b here, except that it depends on age. So since it depends on age, you have n of ta representing the population at time t of age a. And newborn cells, of course, are born at the age 0. So you have n of t0, which is equal to, so be careful here. Either you look at the genealogical case, then you keep only one daughter cell at each division, and you have n of t0 equal the integral of b of a n of ta dA. And you can check that with this boundary condition, the system of equation is conservative. The total number of individuals is conserved. Or you look at the total population, and then you have n of t0, which doubles the number of dividing cells, which so you have the 2 integral of b of a n of ta dA. And this is the major link between the two viewpoints. And you see here, I do not need any approximation. It's not really a mean field limit. It's really directly the equation satisfied in expectation by your random measure. And we can do exactly the same for all structured population equations. I have not cited all the work by the many people who have done that rigorously. And now I do it for the growth fragmentation equation. So now if you assume that your cells divide according to their age, to their size and not to their age, it means that the probability of zeta u, the lifetime, is larger than a, knowing that the size at birth, xu, is equal to x, is equal to, and you see the symmetry, but here you have an intricate game between a and x. It's the integral, is exponential of minus the integral from 0 to a of b taken at x exponential kappa s ds. It's the characteristic curve departing from small x. And similarly, you can show that in average, you have the following structured population equation, which is a growth fragmentation equation. So you have now n of tx, the density of cells at time t of size x, which is given by this equation dtn plus dx of kappa xn. This is the growth rate, plus b of x n of tx. As previously, it's the same as this minus b of a n of ta, and it's the same as for the pure fragmentation equation. Equal what? Equal all the cells which have divided. And here we are in the special case where it is the k of yx of the beginning of the talk, which is equal to 2 delta Dirac in x equal y over 2. So this gives rise to this 4 b of 2x n of t to x. So it's a 4 b of 2x n of t to x if you keep the two daughter cells. And you can check that this part then conserves the mass. But if you keep only one daughter cell at each division, then you don't have a 4 here, you have a 2. And you can check that with a 2 here, it is the number of cells which is conserved. But the mass is not conserved with this. It is conserved maybe asymptotically, but not necessarily at each time point. So here are from our 2 first models. Now I have introduced also another new model, which is the so-called adder model or increment model. The first ones who have written this model, up to my knowledge, it is in 1991, but for totally another applications, Hall, Wake, and Gondal in Journal of Mathematical Biology. But it has been rediscovered in 2015 by Thairi et al., which are biophysicists. So now you have n of t, ax. So here x is the density of cells, the size, and a is not exactly the age, it is the increment of size. Increment of size, it's the difference between the size and the size at birth. So the difference with the normal age is that it grows with the same speed as the size. But it is similar to an age. Why? Because when a cell is a newborn, the increment of size, of course, go back to 0. It is why I have written it as an age. And exactly as for the age model, you have the probability with an increment structured model, the probability that zeta u is larger than a, it is equal to exponential minus integral from 0 to a of b of s ds, as for a renewal process. It is a renewal process, but embedded into a richer model. You have dA over dt, which is no more equal to 1 as for a pure age model. You have dA over dt, which is equal to kappa times x. And you find this equation. So here, you can check why there is an 8 here. It is only due to this kappa x also. So you have d over dtn, so a transport equation, plus d over dA of kappa xn plus d over dx of kappa xn equal minus kappa x bn, the dividing cells, and the newborn cells, n of t0x, which is equal to either 8 integral of x b of a n of t 2x dA, if you keep the 2 cells, population case, or if you keep only one daughter at each generation, then you have a 4 integral of x b of a n of t a 2x dA. And also, you see here the division rates. Before it was a b of x or a b of a, and now it is a kappa times x times b of a, because the division rate depends on the increment, which means that you have a b of a dA. But dA, it is equal to kappa x dt. And this is the reason why you have this kappa x here. Okay. So I was a bit long on the models, but I think it was necessary. And now I apologize for the ones who are less mathematician. I will give some insights, but not many, about the mathematical analysis, which is really a key to estimate properly our division rates. So for the long time asymptotics, it is, I think, since the 1940s or so, that the equations have been studied, and it remains a very active field of research to understand and to have better and finer estimates and better assumptions and more general assumptions and conditions to obtain the long time asymptotics of structured population equations. So to give you a flavor on the simplest case, which is the renewal equation, we can prove that n of TA behaves asymptotically approximately like big N of A, a steady profile, times exponential lambda t, and lambda here is also called the Malthus parameter. It is the first eigenvalue of the system, and you can define uniquely big N and lambda as solution of this very simple equation. So you have dAn, and you have replaced the dTn by lambda times n due to this exponential lambda t ansatz, equal to minus b of a times n, and the boundary condition f of 0 equal to n of a dA. So this is a very good exercise to really have first understanding on what is happening. So you can solve explicitly this equation, and you find n of 0 equal n of a equal n of 0 times exponential minus lambda a minus integral from 0 to a of b of s ds. Okay. And now you have two cases. Either you keep only the one branch case, and then you have lambda equal to 0, or you keep the whole population, and then you have lambda strictly positive, given by the boundary condition here. So you have this condition 2 integral of b of a exponential minus lambda a minus integral of b of s ds equal 1. And this defines you a lambda, which is unique, because you can prove that this quantity under mild assumption on b goes to 0 at infinity. It is decreasing with lambda, and at lambda equals 0, it values 2. Okay. And it is exactly the same kind of behavior for all the other more complex models. But what is different, of course, is to study in detail under which conditions you can obtain such a behavior. Because if you put any parameters, of course, it will not work. So here, typically, I have written it for our specific case. So under proper assumptions, you have that the solution of this equation converges, but it's in reality, I have written it in the case where it is exactly wrong. You will show it in a minute. But normally, if you just take a growth rate which is not exactly linear, okay, so change a little bit kappa x here, or change a little bit the division into two exactly equal cells, and you will find this general fact, which is that n of tx asymptotically behaves like exponential lambda t, so the Malthus parameter lambda, times big N of x, and lambda n being given as the dominant eigenvalue and eigenvector solving this eigenvalue problem. Okay, and you have really very interesting, very recent papers about this. The most recent ones that I'm aware of are, for instance, the work by Bertrand and Watson, who studied precisely cases where this does not always happen, and also two papers by Bertrand Cloès, Pierre Gabriel, and Adeline Merguet, who use probabilistic methods, Harris, for instance, Harris theorem, to prove this type of convergence, and moreover to prove a spectral gap, meaning that this convergence can also hold at an exponential rate. But it happens, a funny fact, which is that precisely the result, which is true in many, in all the important cases, happens to be false in our idealized case of equal mitosis. What does it mean? I've told you the biologists consider that the cells grow at an exponential speed. So you have kappa x here for the growth rate, and you can also assume that it divides almost into two equally sized daughters. But in such a case, precisely, it is a kind of degeneracy. You don't have this convergence towards a steady profile. Look, in this small video, you see, instead of converging to the steady profile given here, the solution continues to permanently oscillate. And why does it happen? The idea is that you can have an intuition about that. If you look at the stochastic process, what is happening is that if you depart from a cell of size x0, then at time t, all its descendants alive along a countable number of lines, which are x0 exponential kappa t 2 power minus something, minus an integer. And so you cannot have a convergence toward a steady distribution if all your cells live in a countable discrete set of lines. And so instead of this convergence, you have a convergence toward a cyclic behavior given, and this is due to the fact that instead of a spectral gap between one dominant eigenvector and the others, you do have a spectral gap, but between a countable number of dominant eigenvectors, given here, and the other ones. So you still have one unique positive eigenvector, but you have a countable set of non-positive eigenvectors given by this formula here. And I refer also to a paper for coagulation fragmentation where it's similar strange behaviors occurred. But you shouldn't care about that. Why? Because in reality, you will never find cells which all grow with the same rate kappa and which all divide exactly in exactly two equally sized orders. And this is the role of variability and heterogeneity in biology. You see, it really gives much more robustness to our phenomena. So now I can finally go to the calibration part, saying that we will use all this asymptotic analysis to estimate our division rate. So typically, you can have two types of methods. Either you have very rich data, and in such a case, you can use all the data at division and not only the data of n of x. Or, and this is the case for bacteria, or you have access only to cells, snapshots of sizes or of ages, generally sizes of cells at a given time point or at several time points. This is the case, for instance, for proteins. This is a more indirect method, and the estimation problem, the inverse problem to solve then, is more ill-posed than in the case where you have richer data, as you can imagine. So yes, so let's go on a little. So also the indirect method, when you observe only n of x, is the only one which was possible for many years before they have developed so extraordinary experimental device in biology. So here it is, for instance, a paper of 1969, I think, yes. And now it's very recent data linked to what I showed you. So what is interesting in this data, you have the two types of data. In green, it is the population data, and in blue, you have the curves corresponding to the genealogical data. And you see the exponential minus lambda a. This is the age distribution. And remember, you have this exponential minus lambda a minus integral of b of a dA. And here you see it is decreasing from the very beginning for the population data due to the fact that lambda is strictly positive. Whereas for the genealogical data, at the beginning, it is almost constant and then it decreases. So it's really the link, but it's experimental data, but it shows how much the models are correct. And this is the type of data you have when you look at both age and size structured populations. So here size, here age, and in color, you have the density of cells. Okay. So just to give you, I will simply give you a flavor of what is happening for the models on the age structured, which allows to understand well what is happening. So here you have n of a. You measure some, you have some noisy measurement of n, and you want to estimate b. So what you can do is, of course, explicitly write this formula b of a equal minus lambda minus n prime of a over n of a. And you see at once that you will need to regularize, because if you have a noisy measurement of n, then the derivative of n will be really too noisy. And this is what you call a degree of ill-posedness 1, meaning that if n is the direct problem is regularizing. If you have b in hs minus 1, the Sobolev space, then you will have n in hs. And so the inverse problem, on the contrary, deregularize in a way. Of course, it's not really relevant for an age measure, because if you are able to measure n of a, you would be able to measure n of 0, and then it's back to a direct problem. Okay. For the size-structured model, things are more intricate, not so explicit. So you have to do two things. You see here the same fact. The derivative of n appears in your inverse problem. So now you want to estimate b. And also you have no explicit expression. So you will need to invert this dilation operator, which gives you 4b of 2x, n of 2x minus b of x, n of x equal blah, blah, blah. And so you have two parts. First, you estimate the derivative of n. You estimate this L of n. And second, so it's the contrary on my slide. First, you solve the dilation equation, meaning that you find a solution f, solution to g of f equal L for a given big L. And second, you find an estimate for big L of n. Okay. So we did this. I skip the details of the solution. The idea is that the dilation equation may be solved, for instance, in more general cases using Mellin transform, and you obtain an estimate which is exactly what we expected, because it is typical for inverse problem of degree of ill-posedness 1. You have an estimate if you have a noise of size epsilon. You have an estimate in terms of epsilon over alpha plus alpha power m, meaning if your underlying function n is in hm. So the optimal error is in as epsilon power m over 1 plus m. I will skip the treatment of statistical data because I have been too long. I'm sorry for this. And just to give you a flavor of a nice inverse problem, meaning are you able, if you want to estimate a division rate which depends on the increment, are you able to use size-structured data to estimate the increments? And the answer is yes, but the inverse problem is really much more ill-posed. It's what is called severely ill-posed inverse problem. So because you see, it's much more indirect. You measure not the total distribution n of ex in such a case, you measure only the marginal n of x, which is the integral of n of ex dA. But despite that, it is possible to find a reconstruction formula which allows you from n of x to estimate b of a. And the result, of course, so I skip the details of the proof, just to tell you that it's possible. It's a joint work with Adélaïde Olivier and Lydia Robert. But the result is not so much so satisfactory in practice. So I think there is still much work to do to improve this estimation, okay? And now just go back to the data to see what is happening when you put all these methods to real data. So this numerical platform has been done by Adeline Fermagnan and also Cédric Doucet. So I really think they have done a great work. So here, so you are, if you can just click on this and you find welcome to the cell division application. So test it, and it is all our methods put together. So now you can, in this interface, you put your data. So here it is. And then you say, I want to try all the models, timer, sizer, adder. The generation time is given by the third column in this file. It's a text file. Sizer division, it's the second column, and sizer birth, the first column. Now you say, yes, my cells grow exponentially, and their growth rate, I put 0.025. And what is the type of data? No, it's not genealogical, this type of data. It's the video I showed you at the beginning. It's the data of this video. I just keep the two daughters and I say submit. And now it's just think, and here is the answer. So with all our estimation methods, we are able to obtain such results. First, the general fact, the best model for this type of experimental data is incremental model. So how can I say that? I compared all the models and estimated the distance with the data. And you see in this, here you have the distribution of lifetimes. Here in black, you have the experimental distribution. And you see that the incremental model behaves very well, whereas the sizer behaves not so well, and the timer not so well either. And here, for the sizer division, both the sizer and the timer and the incremental behave well, but not the timer. Size at birth also, etc. So all these distributions you compare with the experimental data with the model you have chosen. You can compute distances. And finally, and this is maybe the best argument for the incremental model, you compute correlations. And if you think of it, the incremental model is characterized by the fact that the size at birth should be independent of the increment at division. And this is exactly found experimentally. You have birth size increments, the coefficient of correlation is 0. For the sizer, it's not 0, far from that. And for the incremental model, so simulated data, it is of course almost 0. So let's go back. Do I still have some time? I will try to be really, really short on the fragmentation case, because to explain to you what we did for this pure fragmentation equation. The idea is that you can use the same kind of asymptotic behavior as for the gross fragmentation equation, except that it converges to a steady, of course, everything goes to 0, but in a self-similar way. So you have this asymptotics n of tx tends to t power 2 over gamma, g of x t power 1 over gamma, when you take a division rate b of x, which is alpha x power gamma. And the first idea was to use this asymptotic profile. But in practice, even if we have a theoretical result saying that it should be possible to use the asymptotic profile, in practice, it doesn't give you anything really useful, because it depends too much, the formula we have, the problem is too ill-posed, and the formula depends too much on the behavior of the self-similar profile around 0 or around infinity, which are precisely the places where you have experimentally no information. So we did it differently. We used the time dynamics and used the fact that you have this t power 2 over gamma, asymptotically speaking, so that when you can look at the moments of the equation and find, so what's the good slide, and estimate how it converges to a steady profile, and then you estimate gamma, and from this gamma you estimate alpha. Typically, this is the kind, you look at the mean length, and you just really very simply estimate it with such a curve c t power minus 1 over gamma. So it's extremely cheap, numerically speaking. So it's what is interesting when you study the asymptotics. It really allows you to gain much time in terms of numerics. And only with these two parameters fit, you are able to fit extremely well. So here you see for 4 different types of proteins, you have, what did we do? We departed from the experimental initial condition at the top for each protein. We had estimated these 2 parameters, alpha and gamma, typical of fragmentation, of the fragmentation rates, separately. And then we go on all these curves. In the comparison, you see, you have the histograms for the experimental data, and you have the plane curves for the simulated data, and it fits extremely well, only with these 2 parameters, alpha and gamma. But for the fragmentation kernel K0, our problem is you can take several different K0, and they will all fit relatively well, all these curves. This was a kind of bad news, meaning that with this type of data, it's not really possible to decide which fragmentation kernel K0 is the best. But we think it's possible to develop new methods typically using not the asymptotic behavior this time, but on the contrary, using the short time behavior. And this is the comparisons of p-value when we test, are the distributions significantly different from one another? So meaning, are we able to say something about the fragmentation kernel which is different? The answer is, you see, is yes, as soon as you depart from very peaked initial condition. And then it's possible to see the influence of the fragmentation kernel on your distribution. So I'll stop here. I hope I will not too long. It's just to tell you that I think we are now able to do many things, but many problems, more interesting yet, remain open to maybe to generalize to other type of population, of structured populations, to other types of biological questions. Also, we need to develop tests, statistical tests, to really quantify better which model is the best. We have done some things, but it's not yet fully rigorous. And I think we need to analyze this, the tests we have built. We can incorporate variability, memory, interaction between cells, etc. So thank you very much for your attention.